The Poynting theorem is a statement of conservation of power for electromagnetic waves. Let's draw a situation so we can look at all the places that power can go electromagnetically. So let's say we have some sources, Ji. I is for impressed here, which just means sources. And we'll constrain our view to a particular volume. Now these sources could be radiating. There could be electromagnetic waves entering or leaving the volume, so that there could be power that is entering or leaving that way. There could be power being dissipated in materials inside the volume, and there could be power being stored in the electric and magnetic fields, especially around the sources. How do we account for all of that mathematically? Using the Poynting theorem. I'm going to derive the Poynting theorem for you starting from Maxwell's equations. So, we start with Faraday's law. And Ampere's law. Now, Ampere's law is usually J omega epsilon E plus J, and we have two types of J here. We have the impressed currents, Ji, and we also have conduction currents, Jc. Remember that conduction current, Jc, is sigma times the electric field, where sigma is the material conductivity. The way we start doing this is we're going to take advantage of a particular vector identity, and that is that the divergence of the cross product of two vectors is equal to curl of A dot B minus A dot curl of B. So if I'm talking about the complex Poynting vector, S, which is 1/2 E cross H star, if I take the divergence of that, then that would be taking the divergence of 1/2 E cross H star, then I should get 1/2 curl of E dot H star minus E dot curl of H star, like that. Now, just as a reminder, star stands for complex conjugate, so that's the complex conjugate of the phasor magnetic field, H. How do we get from these Maxwell's equations to here? Hopefully the clues are all right in front of you. The first thing we have to do is dot Faraday's law with the complex conjugate of the magnetic field. And then we also need to dot Ampere's law. Whoops, we need to dot the complex conjugate of Ampere's law with the electric field. So once we do that, we can subtract the two. We're going to subtract the top one from the bottom one. So then we have E dot curl of H star minus H star dot curl of E equal to j omega mu magnitude h squared minus j omega epsilon magnitude e squared plus E dot Ji, the impressed currents, Ji star, sorry, plus sigma magnitude E squared. We're almost there. We apply that vector identity, and we get that the left-hand side is equal to the divergence of E cross H star, the negative of that. And because the Poynting vector has a factor of 1/2, we're also going to divide by 2. So let's put a 1/2 right there. So on the right-hand side, we also have to divide by 1/2. I'm sorry, we have to divide by 2. So then we're going to have 1/2 E dot Ji star plus sigma over 2 magnitude E squared plus, I'm going to write this in a particular way that'll become clear in a minute, 2j omega mu over 4 magnitude h squared minus epsilon over 4 magnitude e squared. All right, close parentheses. The reason I've written those that way is because the magnetic stored energy density, that's a lowercase w, m, is equal to 1/4 mu magnitude h squared. And the electric stored energy density is 1/4 epsilon magnitude e squared. We talked about those in 331 when we talked about the stored energy in an inductor or in a capacitor. And you can refer back to those discussions for where those came from and why there's a factor of 1/4 on there. So these are stored energy densities. Also interesting is this factor of j omega on the front of that part of the equation. That's a time derivative, which makes sense because this is a power conservation thing, and we're talking about power in all the other terms. So the time derivative of energy is power. This is power dissipated as loss, and this is power from the sources. So it makes sense to talk about this in the context of a volume, like I drew at the beginning. So let's take the volume integral of the whole thing. On the left-hand side, we're going to apply the divergence theorem. So the volume integral of a divergence turns into a flux integral of whatever the thing was you were taking the divergence of. So now we have the surface integral over the boundary of the volume of the complex Poynting vector dotted with the differential surface area. And there's still a minus sign on the front of that. And that turns out to be equal to the volume integral of all of these other things. Actually, I'm just going to evaluate those and turn them into their associated powers. So the source power, that's power in, plus the power that's dissipated as loss within the volume, plus 2j omega big Wm minus big We. So those are the total stored energies in the volume. So that's the thing. We've got source power, we've got loss power, we've got energy that is either entering or leaving storage in the electric and magnetic fields within the volume. The thing that's left is the Poynting vector. And that is power entering or leaving the volume in a wave. All right, so this is the complex Poynting vector, right? So this left-hand term is complex. I want to point out the types of other terms that we have here. The stored energy time derivative term is purely imaginary because these stored energies are real. Remember, there was a magnitude h squared and a magnitude e squared. So those are real quantities, which means that this whole thing, since there's a j omega in the front, that's imaginary. These other two powers are real because we have an input power and a loss. So those are real powers, which means that if we're talking about the time average quantities, like the time average Poynting vector, which is just the real part of this complex Poynting vector, if we want to talk about the time average Poynting vector, which I'll write it down again is 1/2 the real part of E cross H star, which is just the real part of the complex Poynting vector. In that case, we don't really talk about these stored energies in the volume. We're just talking about the power that's being input and being dissipated as loss. And that's the thing that we're talking about when we're talking about antennas. So for an antenna, we can say that minus this surface integral of the time average Poynting vector is equal to the power in plus the power being dissipated as loss. In the materials within the volume. And since often we're just talking about free space, that loss term goes to 0 too. No loss in free space. Now the signs on this are such that power leaving this thing will be negative because of the negative sign on the front. And power entering would be positive. And same thing for the input power. So power added to the system would be negative, or removed, or would make it act like a loss. So that would be positive again. So when we're writing down our sort of power budget equation for an antenna, we can just say that this integral of the time average Poynting vector of some volume that surrounds the antenna is equal to the power that is being input, the power that is being radiated by the antenna if there's no loss. That's all there is. So if we have Pn plus P loss accounts for any power that gets lost in like the materials of the antenna or anything like that. So that is the Poynting vector for you in a nutshell. It just tells us where all the power is going here. Most of antenna engineering boils down to that in the end. Is there enough power to get the signal where it needs to go?